This is part 1 of the lectures on dot product. We continue here to consider the coordinate-free definition of the vector. And in the coordinate-free definition, the vector is a directed line segment. We can recall what that means. By line segment, it means it's a straight line, it's linear, and it has a finite length. By direction means it's pointing at a certain direction in space, whatever the space may happen to be. But the vector is not tied to any coordinate system, it's not tied to the origin of any coordinate system, and so it is considered coordinate-free. In the previous lecture we talked about scalar multiplication of vectors. Here we're going to continue that discussion and look at another way to multiply vectors. So in general, there are 3 ways to multiply vectors. The first is a scalar multiplication. All right, alpha is considered a scalar here, and all that changes is the length of the vector. If alpha is less than 0, the vector then points in exactly the opposite direction. That is scalar multiplication. The one we're going to talk about now is dot product. The result of a dot product is that 2 vectors subjected to the dot product end up being a scalar. The result is a scalar. The other way to multiply 2 vectors is the cross product, and the result of the cross product is another vector. For these reasons, the dot product is sometimes called the scalar product. And the cross product is called the vector product. We can also recall that for numbers, the dot is equivalent to the cross, gives you the same, 6. Okay, no difference with numbers. It's just notation. But in vectors, the dot and the cross product mean very different things and have very different results. The general coordinate-free definition of the dot product is that the dot product is the product of the magnitude of the 2 vectors, magnitude of u times the magnitude of b. That would be the length of u times the length of b. Both are just scalars, times the cosine of the angle between them. And the dot product has its very famous application, and that is to the calculation of work. In trigonometry, we often just compute f times the cosine of theta to give us the magnitude of the force in the direction parallel to the displacement. So in this case, here's the displacement. They wrote the delta there, which was unnecessary. We'll cross it off. So this is a vector r. And the f cross theta is part of the projection, well, later we'll talk about projection, of the force onto the direction of the vector r. And then work is the dot product between them. So here we have an equation for work in terms of dot product. Another name for this component, of course, is the force parallel to the displacement. The dot product gives us many results, and one of the most important ones is this idea of orthogonality. Remember orthogonal, perpendicular, normal. Those are vocab words from earlier in the semester, as in earlier meaning about 2 days ago. Okay, so if you have 2 vectors that are orthogonal, oops, sorry, well, let me get rid of that. Okay, so, sorry. So we have u, well, this is not working. Okay, u is perpendicular to v. They are at right angles. That means the angle between them is either pi over 2 or 3 pi over 2. then by the basic definition of the dot product, their dot product is 0. So we have these basis vectors, we remember in the IJK coordinate system. All of these are mutually orthogonal. So I dot j, I dot k, and j dot k are all going to be 0. We're going to use this later to develop the coordinate approach to dot product. When using the coordinate-free approach to vectors, the fact that the dot product is 0 is, well, it's interesting. It's just part of the definition. But later, when we have the vectors in terms of components, it's not obvious that they are at right angles or even what the angle is between them. In that case, the dot product becomes a test for orthogonality. This symbol here was just supposed to be an arrow, meaning implies, but it seems to have some extra equal sign with it. I'm not sure how that happened. At any rate, the test is that if the dot product between two vectors is 0, the vectors are orthogonal. Now, if we looked at orthogonal vectors, what about vectors that are parallel or anti-parallel? In that case, the cosine of the angle between them is going to be 1 or minus 1. So u dot v is equal only to the magnitude of u times the magnitude of v, means that the vectors are parallel. If there's a negative sign involved, it means they're anti-parallel. Of course, that's not really a good test for parallel or anti-parallel. What this is used for most is to find the magnitude of a vector. So look at two vectors that are, well, the most extreme case of being parallel. If they are the same vector, they absolutely are parallel. So here is a dot product of a vector with itself. Cosine, of course, is 1. That's the value of 1. So v dot v is the length or magnitude of the vector squared. You can turn that around and write an equation for the length of the vector in terms of the dot product of the vector with itself. Again, many of these things are going to be used more when we have coordinates, but they're developed here with no coordinates in mind. Now let's look at the idea of a projection. A dot product is often referred to as a projection, and this is why. Let's say that you're taking the dot product of a vector u, and the other vector is a unit vector. So in general, u dot v hat would be the magnitude of u times the magnitude of this unit vector times the cosine of the angle between them. Well, the magnitude of a unit vector is 1, so this just reduces to the magnitude of u times the cosine of theta. And here's a dot product onto the basis vector I. So again, the magnitude of I is 1 because these basis vectors are unit vectors. And if this is the angle between them is theta, this is often called the projection. It's called Vx. It's called the component when we're talking about the vectors, the basis vectors, but in general it is the projection of V onto the direction of I. We aren't restricted to unit vectors along the coordinate axes to take the projection. We can take a projection of U onto any vector onto any direction. And there's actually a two-step process for it. I like to think of it in terms of the two-step process, but it's often written as one step. And you might have seen this before, and here's the one step right down here. But what do these steps mean? Say I have a vector in a certain direction. Okay, so this is going to be my vector v going in this direction. And from that, I only want the direction of v. I don't care about its magnitude. So I create a unit vector out of v. Now what's going on here? we mentioned this before with scalar multiplication, but sometimes we have to see it in a different context to really put the pieces together. The magnitude of the vector is a scalar. Now let's assume right now it's not 0, and other than being 0, it's going to be positive, right? It's the length of the vector. So I can create out of it a fraction, right, and multiply the vector by this scalar. So here's my vector, here's my scalar, multiplying the vector v. You can write it like that. And the result is that we now have a vector that has a length of 1, but points in the same direction that v pointed. Let's verify that. We now know how to take the length of a vector. So the length of a vector, I'm just going to write one line for simplicity with this pen that I'm using. It's a square root of the vector of the dot product of the vector with itself. So if I want the magnitude of that, got v over magnitude of v. Okay. I'm sorry, that's, yeah. Let's do it square, and we'll take the square root later. Now I have v over the magnitude of v dotted with v over the magnitude of v. All right, those are just scalars. So the denominator just scalars, that comes out as the magnitude of v squared here, and I have v dot v in the numerator. Okay, that's simply the magnitude of v squared. I said I was going to draw one line, and then went ahead and drew two. All right, that's one. So that's the magnitude of that vector is indeed 1. It is a unit vector. Okay. Now that unit vector is shown here as a unit vector in that direction of v. I'll take the projection of u onto that unit vector. It's just the dot product. So that's what happens here. Take the projection of u onto that unit vector. We can write it like that. Often this is written, as I said, in one step, and here's what the steps mean. You've taken u and you've dotted it with a unit vector in the direction of v. So the terms here, whoops, sorry, wrong tool here. That gives you your unit vector. And the result of that, because it's the dot product, is a scalar. So the length from here to here is, I'm calling u, projected onto v. Now that was the scalar projection. There's also something called a vector projection. Be sure to make a good distinction of this. This difference, scalar, vector. In fact, through this whole class, it's required to make a very good distinction between what is a scalar, what's a scalar output, and what is a vector. So this is, in a sense, also more practice in that area. Before we had a scalar projection, now we have a vector projection. What we mean is that we don't just want the length of u, the projection of u in the direction of v. In fact, we want a whole new vector pointing in that direction. So I like to think of this as a three-step process, although it is also often written just like here, in one step. So let's go through the 3 steps so that we have a good grasp of what's going on here. We have our vector u, and we want to find a vector projection of it in the direction of v. So we take v and we make it, as before, into a unit vector. To do that, we take v and divide by its magnitude. Then we take the dot product of u, which gives me whatever scalar projection of u onto the direction of v. What will this be? This is the scalar. It is going to be the length of that new vector that I'm looking for. It was, as before, u onto v as a scalar. It's only the length. Now I want a vector. In other words, I want to take this uv, I have a length, and now I need a direction to make it into a vector, so I have to multiply it by a vector. Well, you multiply it by the unit vector that you created earlier. Remember, this is just scalar multiplication because all of this is a scalar. So you are rescaling that unit vector v, it kind of left it up here in the diagram, by this projection and getting out of that a new vector. So here's the one-step process, and it's correct, of course. All the steps are put together there, but it kind of obscures how it came about. U dot v divided by the magnitude of v created the scalar projection. V over the magnitude of v is a unit vector in the direction where you need the vector projection to be. We're going to list now some of the properties of the dot product, and in a sense we're comparing this dot product to what we know from algebra. You can recall that from algebra we had properties of being commutative, distributive, and associative, and these will apply. Some of these apply and some of these don't. The first property is that the dot product is commutative. It's important to state this. Well, first, it's a useful result, but also to remember that not everything in these vector operations is commutative. For example, the cross product that we do next will not be commutative. In fact, it will be anti-commutative. But this is commutative. How does this follow from the definition? Okay, the definition of u dot v is just the product, multiplication, of the magnitude of v, scalar, magnitude of u, another scalar, cosine of theta, another scalar. This is just like multiplying 2 times 4 times 6. Well, cosine theta can't be 6. We'll put that as 1. All right, you just multiplied 3 scalars together. The result is it's a scalar, but you could multiply 2 times 4 times 1 in any direction. It is commutative. Therefore, because of the definition, the dot product is also commutative. We can use the same property to show that the dot product is distributive. But now we come to some differences. It is not associative with respect to dot product. And the reason for that is that you can't even define, let's write what distributive or associative means. If I have A times, I'll use that for times, B times C, I can do these in any order. I can go A times B and then multiply C, or any other arrangement I would like. I can associate any of the terms together. Look at dot product. We can't even define this because the outcome of this dot product is a scalar. And a scalar cannot be dot product, cannot be part of a dot product. Dot product is between two vectors. So by taking the first dot product in what we're trying to do here, we've created a scalar, and the whole thing can't even be defined. The scalars themselves, though, can move around through the dot product, and you can work that through using the basic definition. Now here are two more properties that are interesting. In the real numbers, we have an identity, which is 1, so that 1 times any scalar alpha is equal to alpha. In dot product, there is no vector. Say vector 1, we'll make it be a vector, dotted with v, so that the result is v. Because this is a scalar, and this is a vector, and vectors and scalars aren't equal to each other. So there's no identity at all. Now let's look at the 0. We use the idea that there is a unique 0 in numbers in order to cancel. I have something like 4 times x equals 4 times y. I can cancel the 4's, or in essence I can write 4 x minus y is equal to 0, and the only way this holds is if x minus y is 0, which means that x is equal to y. Or if you look at cancellation, you cancel those two and you get x equal to y. For the dot product and later on for the cross product, this doesn't work. This is a important because it might be a test question. All right, if we have u dot v equals u dot w, it can be written as u dot v minus w equal to 0. Okay. What does this mean? It only means that u is perpendicular to the vector v minus w. So this will hold for any vector that is perpendicular to u. It doesn't have to be 0. It could be 0. We're going to assume here that u is not 0. Otherwise, of course, it's, another case. It is possible that v is equal to w, in which case v minus w is the 0 vector, so u dot the 0 vector is equal to 0. Okay, and that's similar to the case up here, but it's not the only case. We can have u perpendicular to v minus w, and this can be any vector that's perpendicular to u. If we could cancel, it would look like this. Cancel those, and we would have v equal w, but that is not the case because there's no cancellation, because there is no unique 0, right? Unique vector that gives a 0 result to dot product. 2 slides back, we talked about the distributive property of dot product, and it looks like this. U dot v plus w equals u dot v plus u dot w. So that's the distributive property, and we never proved it. If we were working with components, it'd be easy to prove, but we wanted to prove it for the coordinate-free case. And we can prove it just with a picture. This is a graph showing vector addition. So this is coordinate-free vector addition, where we just put the vectors, tip to tail, or vice versa. So here's our vector b, and we had a vector c, and by putting c at the tip of b, we create that product b plus c. Now let's look at the projection of all 3 of those down onto some vector a. This is, should have used the notation like this. A dot b plus c, this is what we want to prove, is equal to a dot b plus a dot c. And the projection of b onto a is b sub a here. The projection of c onto a is just this length. Okay. Note that this is written where the c is way up here. Here, it's very easy to see. That's the angle theta. What is the angle between b and c? Well, you'd actually have to move the vector down. It's possible to do that because vectors can move in space, and find that angle. So here would be our vector c. It's about right. And this would be the angle between it. So here's another one, theta with respect to c. Okay, and that projection could be obtained, but we can see that that would be exactly the same as the projection from c to a when c is sitting up here. Now look at b plus c. There we go. It's because how we arranged the vectors tip to tail, and then b plus c connected the tail of b to the tip of a. And that is a proof in pictures. We could have written out all the steps, but here you go. I think it's clearer to see that, especially if I take all of the writing off of there. So that's it, the distributive property in pictures. So that's the end of this lecture. For the next lecture, we'll look at the coordinate approach, and then we will prove some important theorems and do an interesting problem or two with dot product.